Our next application of the derivative takes us all the way back to the beginning of the quarter when we were doing limits. Remember, we had limits like sine x over x as x goes to 0. The thing is, this looks like a 0 divided by 0 if you were just to plug that x in, and so 0 over 0 always signaled we had more work to do. Same thing here. You plug a 3 in, x squared minus 9 over x minus 3. Again, that looks like a 0 divided by 0. And here we had pretty straightforward thing to do of factoring and canceling. Up here, we had to make a different kind of argument as to what how to calculate this limit. And I know that when I present this, I almost always say, well, look at the graph of the numerator. Right? This is a sine curve. Looks like this. Look at the graph of the denominator. It's y equals x. Right? And I make the argument that if you zoom in really close to the origin, they're both passing through the origin with slope 1. And so if you're looking at the y-coordinate on the sine divided by the y-coordinate on the line, I made it look like the red line was below the blue, but actually it's the other way around. But for each value of x here, those two y values are very close to the same. And in fact, the closer x gets to 0, the closer those two y values are to the same thing. And if you're taking a limit, you're taking a ratio of those two y values, then if they're pretty much the same number, the fraction is pretty much 1, and it turns out that this limit is 1. Okay. This is the idea I want to look at closely here for lHospitals rule. So, in fact, if we had lHospitals rule way back in the beginning, these would have been pretty easy to do, except we didn't know how to take derivatives, so really it doesn't help us much. Wouldn't have back then. But now we do know how to take derivatives. So here's the situation. The idea is that if you have a function that's differentiable, it has a derivative, it has a uniquely defined tangent line at every point, then the more you zoom in on it, the more it looks like a straight line. So if we're in a situation, if we're looking at a limit as x goes to c of f of x divided by g of x, and the limit of the numerator, the limit as x goes to c of f of x, is 0, and the limit of the denominator is 0, the limit as x goes to c of g of x is equal to 0. So you're in one of these 0 over 0 situations. Then what we're going to do is we're going to focus on the derivatives. All right? And this is lHospitals rule. L'Hôpital was French, so the spelling is, you'll see it differently in different books, but anyway, lHospital is the way I spell it, and a lot of books will do it that way. So if you're in a 0 over 0 situation, when you're taking a limit, then what we can do is this: the limit as x goes to c of f of x divided by g of x is equal to the limit as x goes to c of f prime of x divided by g prime of x. So I'm looking at the limit, the ratio of the slopes rather than the ratio of the y values. And let me give you an argument as to why that might even be true. The thing is, you've got some value of c here, and because the limit as x goes to 0 of x goes to c of f of x is 0, that means whatever that function is at x equals c, it's essentially passing through 0, right? So likewise, you've got this g of x, which its limit is also 0. So as x gets close to c, this is essentially passing through 0. Now what happens at 0, I don't actually care, but at least as you get close, this is what it looks like. And these may be bent, they may be whatever, but the more I zoom in on it, the more they look just like straight lines. Okay, so when I'm looking at the ratio of this y value divided by this y value, then I claim what I can do is I can look at the ratio of the slopes. So for instance, if I look at this slope here on the blue line, rise divided by run, in fact I'm going to call it rise 1 divided by the run. And then I'm going to divide that by, in green here, this rise divided by run. And so I'm going to call that rise 2 divided by the run. Now, it's the same run in both cases. For this x value, the distance away from C is the same no matter which y value you're doing. So the slope of the blue line divided by the slope of the red line looks like this. Well, how do you divide fractions? You invert and multiply. So this is equal to rise 1 divided by rise 2 because the runs cancel out there. When you flip it upside down, this run and that run cancel out. And so this is saying this is the ratio of the y values. This is the ratio of the slopes. So the ratio of the y values is essentially the same as the ratio of the slopes. This is because you both go into 0. Okay? And this is what L'Hopital's rule is. So let's see how that helps us with those two limits that we had up above. So for instance, if I look at the limit as x goes to 0 of sine x divided by x, this is by L'Hopital's rule. And this is a notation that you'll see in some books. I use it all the time. This is just a little dot over the equal sign. This, to me, it's an indication of, hey, this is not just algebra that we're doing. There's something more going on here. Okay. So L'Hopital's rule says if you're in a 0 over 0 situation, which I am, if I plugged a 0 in there and a 0 in there, both numerator and denominator are 0, it says I can take the derivative of the top, derivative of sine x is cosine x, and take the derivative of the bottom and make a new fraction. This is not the quotient rule. This is L'Hopital's rule. I'm not taking the derivative of this function. I'm taking the limit of this function by taking the derivative of the top and the derivative of the bottom. Right? And so then we approach the same place. This is the limit as x goes to 0. This is the limit as x goes to 0. And now I'm not in a 0 over 0 situation. When I plug a 0 in now, this is the cosine of 0 divided by 1, which is 1 divided by 1, and so the answer here is 1. Anytime you have a 0 over 0 situation, when you're trying to take a limit, you have L'Hopital's rule. That will help you out. So for instance, on that second one, the limit as x goes to 3 of x squared plus 9 over x minus 3, right? Back in the beginning of the quarter, we would have factored that to x plus 3, x minus 3. The x minus 3s would cancel out. So I'd had left with an x plus 3, and the answer is 6, right? Whoops. It's 6 if I had written the problem down right. There we go. Now that factors into x plus 3 and x minus 3. Let's see how L'Hopital's rule handles this, because it is a 0 divided by 0 situation, and I'm going to take the limit as x goes to 3. Put a little dot over there just to indicate this is L'Hopital's rule. Take the derivative of the top, 2x. Take the derivative of the bottom, 1. Wait. Why do I do this? Why do I do this? The point is the limit as x goes to 3 there. It's going to be the limit as x goes to 3 here. It's the same place here or there. You probably saw that I had made that mistake already, and you're saying, Will, go back, erase that. Well, here we are. This is limit as x goes to 3. I've taken the derivative of the top. I've taken the derivative of the bottom. Now I can plug the 3 in, and I've got 6, right? 2 times 3 over 1, which is 6. And we end up with the answer that we got before, right? Very nice, clean way of doing these 0 over 0 situations. I want to do one more for you in this video, and then we got some more examples to do in a later video. But let's take a look at the limit as x goes to 0 of 1 minus cosine x over x. Now this is one that we made an argument for earlier in the quarter because we needed it in order to take the derivative of the sine curve or the cosine curve, probably both. So we had a value for this, but let's see what we get here, right? If you plug a 0 in, this is definitely a 0 on the bottom, and it's a 1 minus 1 on the top, so it's a 0 on the top. So by L'Hopital's rule, this is the limit as x goes to 0, so same thing here and there. Take the derivative of the top. Well, the derivative of 1 is 0. The derivative of Negative cosine x is positive sine x. Take the derivative of the bottom, that's 1. And this is not the example I wanted to do, but okay, we're doing it. So this is the sine of 0 over 1, which is 0 over 1, and this one is in fact 0, so that is what we had before. Now, let's do the one I really wanted to do. I want the limit as x goes to 0 of 1 minus cosine x over x squared. That's what I wanted. So here we go. Again, it is a 0 over 0. You plug a 0 into the top, a 0 into the bottom, you're going to get zeros. So this is the limit. This is by L'Hopital's rule, the limit as x goes to 0. Take the derivative of the top. Well, it's the same as it was up there. Now the bottom has a different derivative because it's a different denominator. So we've got derivative of x squared is 2x. Right? Again, I'm not doing the quotient rule. I'm doing L'Hopital's rule. Derivative of the top, derivative of the bottom. What do I have now? I have 0 divided by 0, don't I? Well, what can I do? Well, what I can do is I can say, well, wait a minute, I'm in a 0 divided by 0 situation. L'Hopital's rule applies. So let's try applying L'Hopital's rule again and see what I get. So this is the limit as x goes to 0 of derivative of sine x is cosine x. The derivative of 2x is 2. Definitely don't have a 0 over 0 situation now because that denominator is a 2. And plugging the 0 in, I've got the cosine of 0 over 2. Cosine of 0 is 1. So my answer here is a half. Right? In fact, it's so powerful that I need another video to show you all the different things we can do. So let's leave this one here and we will look at some other examples in the next video.